Good afternoon, students. This is Dr. Green. This recording, integrity recording, is for Chapter 11, and it deals with understanding statistics in research. I know that you have had a undergraduate statistics course already, and what we'll be talking about will be many statistics that you may be familiar with, some that you will not be familiar with. I am trying only to reinforce the ones that you are familiar with. Here are our objectives. Identify the purposes of statistical analyses, describe the process of data analysis, describe probability theory and decision theory that guide statistical data analysis, describe the process of inferring from a sample to a larger population, discuss the distribution of the normal curve, that should say curve, compare and contrast type 1 and type 2 errors, identify descriptive analyses. Describe the results obtained from inferential statistical analyses. Describe the 5 types of results obtained from quasi-experimental and experimental study designs. Compare and contrast statistical significance and clinical importance of results, and critically appraise statistical results, findings, limitations, conclusions, and generalization of findings. So understanding statistics and the analysis of statistical findings is very important for understanding the results of quantitative reports. Statistics can be used for reading or critiquing published research, examining outcomes of nursing practice by analyzing the data collected in a clinical site, developing administrative reports with support data, analyzing research done by nursing staff and other health professionals at a clinical site, and demonstrating a problem or need and conducting a study. So why is critically appraising the results from quantitative or outcome studies so important? You should be able to, at the end of this course, be able to identify and understand the statistical procedures that are used in a study that you're reading about. You should be able to judge whether these procedures were the appropriate ones for the purpose and hypotheses, questions, or objectives of the study, and for the level of measurement of the variables. Determine whether the researcher's interpretations of the results are an appropriate evaluation of the clinical importance of the study findings. What are the stages in data analysis? Prepare the data for analysis. Describe the sample. Test reliability of measurement methods using Cronbach's alpha. If less than 0.7, the researcher will probably select another instrument and remeasure using that other instrument. Conduct exploratory analysis. Conduct confirmatory analysis guided by the hypotheses, questions, or objectives. And conduct post hoc analysis. How should the researcher prepare for data analysis? Well, there are 5 steps. Enter the data into the computer using means designed to reduce errors. Clean the data to ensure accuracy. Look for data entry errors and missing data. Correct all identified errors, identify missing data points, and add missing data when possible. What are the 2 major types of statistics used in nursing studies? The 2 major types are descriptive and inferential. With descriptive statistics, we are describing or summarizing the sample and variables. With inferential statistics, we are inferring or addressing the objectives, questions, and hypotheses. Inferential statistics are hypothesis-driven. They provide a number the researcher interprets to infer probable truths for the population. And they assist in identifying relationships, examining predictions, and determining group differences in studies. Descriptive statistics are also referred to as summary statistics. They help determine predominant data, average values, sameness, and differentness. In any study in which the data are numerical, data analysis begins with descriptive statistics. So you know when you're reading a research report and you get to the findings, they will always say how many were the N, how many were in the study, how many men, how many women, what their ages were, what the average age was, etc. In simple descriptive study, the analysis may be limited to descriptive statistics only. So in a research report with inferential statistics, you will see data presented in this order. First, the sample description, the demographic data, descriptive analysis of the variables, and then the inferential statistics. The types of descriptive statistics. This I am sure you had in your Essentials undergraduate statistics course. Frequency distributions, measures of central tendency, and measures of dispersion. So in an experimental design, these three measures that we just talked about in the previous slide are presented for each group in the study to help compare groups for similarity. Remember, the groups have to be similar to start with. Otherwise, how do we know that the treatment actually made a difference? Maybe that group was different to start with. So the rationale, if they're similar to start with, then the researcher can say the intervention made a difference if they find a difference at post-test measurement. Tailedness. Here we are talking about the normal curve. So an extreme score can occur in either tail, on the left or the right, of the normal curve. An extreme score is higher or lower than 95% of the population. Mean scores of the population also can be extreme and occur in the tail of the normal curve. If the mean score is an extreme value, the population is not likely to be the same as that represented by the normal curve. It is significantly different. However, extreme values that are members of the population do occur. Thus, there's always a risk of making an error in deciding that the groups are different. Two-tailed test. Assume that an extreme score can occur in either tail of the distribution. A non-directional hypothesis, we went over this earlier, tests for significance in either tail, right? The researcher says that there's a difference, but they don't say whether it's greater or lesser. The hypothesis, the extreme score is higher or lower than 95% of the population. Thus, the sample with extreme score is not a member of the same population. A two-tailed test of significance is used. So here is the normal curve that you learned about in your statistics course. So here we have a hypothetical curve with all these values under the curve, And we have one standard deviation from the middle score to the left and one standard deviation to the right. A second standard deviation to the left and a second standard deviation to the right. These are the tails, the green area. Okay, so if you have a score here or here, right, it means that it's different from 95% of the population. Let's go back just a little bit. This is number 20. Let's go back. We were talking about measures of central tendency. One of the ways that data can be displayed, here is an example of what we call ungrouped frequency distribution. So the data are presented in raw counted form. So let's say that how many people got a score of 1? 1. How many people got a score of 2? 1, 2, 3, 4, 5. How many people got a score of 3? 1, 2, 3. How many got a score of 4? Only 1. And how many got a score of 5? Only 2. Okay, so they're just simply counted, and there's no grouping. Now, this is an example of grouped frequency. The data are pre-grouped into categories to display the frequency of the ranges in each category. So let's say in our study, hypothetical study, there were 14 people who were aged 22, 39, 43, aged 40 to 59, 26, age 60 to 79, and 4, only 4, from age 80 to 100. Okay, that's an example of a grouped frequency distribution. This is an example of percentage distribution. 41.7% has to do with salaries, 88.3% has to do with maintenance, 16.7% has to do with equipment, 8.3% has to do with fixed costs, and 25% has to do with supplies. Many times when someone is presenting data, they will use the column approach here or the pie chart. Okay, so in the pie chart, each slice of the pie is a different color, right? So one of the larger slices is this green one over here, right? This has score 5, and there were 28%. Whereas it looks like the pink slice of the pie is someone with a score of 1, and that represents 8% of the 100% pie. The same data can be put in a column or vertical form. Pie chart is very, very useful. So we'll talk about measures of central tendency, mean, median, mode. So the mode is the numerical value or score that occurs with the greatest frequency, which you know that. The median is the midpoint or the score at the exact center of the ungrouped frequency, the 50th percentile. Okay. The mean is the average, the sum of the scores divided by the number of scores being summed, the average score. So here we have the normal curve, right? The median score is right here at 0 point, right? Here we have the first standard deviation, second standard deviation. This represents 34%. This represents to the left, 34% to the right. And then the second standard deviation, and the third standard deviation. Anything that's out here in the tail is the farthest away from the mean score. So they are very different from the average score. So the mode is used for nominal data. It's the numerical value or score that occurs with the greatest frequency. It's expressed graphically and is not always the center of the distribution. So here we have a distribution, a curve that shows scores, right? And let's say this is 0 and this is 100, right? It's bimodal. So you have a very frequently occurring score here and a very frequently occurring score here. So let's say this was represented class grades of a class, right? The class looks like they're pretty evenly split between low scorers and high scorers. The median. This is used for ordinal data. It's the value in the exact center of ungrouped frequency distribution. It's the middle value. It's obtained by rank ordering the values, and when the number of values is uneven, it may not be an actual value in a data set. The mean, it's used for ratio and interval data. We know that it's the average, right? The mean may not be a data set value. If a one-group pre-test, post-test study uses subjects as their own controls, which is the study design? Experimental, quasi-experimental, correlational, or descriptive? The answer is B. The purpose of quasi-experimental and experimental designs is to examine causality. Okay, when you use a one-group pre-test, post-test, with the subjects as their own controls, it's only quasi-experimental. If it were experimental, we would have to have a control group and an experimental group, correct? We'd have to have at least two groups. Measures of dispersion. So this is a measure that indicates the amount of differentness in a data set. Range, variance, standard deviation, standardized scores, and scatter plots. So the range is the spread between the highest value and the lowest value. For example, ages range between the number 65 and the number 85. That's the range of, let's say, the participants in a study. It's obtained by subtracting the lowest score from the highest score. It uses only the two extreme scores, both ends, and it's a crude measure, and it's sensitive to outliers. Difference scores is the sum of all different scores in a data set is 0, making it a useless measure. I don't think you'll see a lot of this in your nursing studies. Difference scores are the basis for many statistical analysis procedures. I don't think I've ever seen different scores in a nursing study. They are obtained by subtracting the mean from each score, and sometimes referred as a deviation score because it indicates the extent to which a score deviates from the mean. Standard deviation is another measure of central tendency. It's the square root of the variance. Just as the mean is the average value, the standard deviation is the average difference score. Standardized scores are raw scores that cannot be compared and are transformed into standardized scores. Common standardized score is the z-score, and it provides a way to compare scores in a similar process. a scatter plot. We'll talk about this for a minute. It's a visual representation of the data on a scaled graph. So you'll have two axes, a horizontal x and a vertical y, and it helps you to illustrate a relationship between two variables. For example, height would be on the x and weight would be on the vertical. Okay, so we have the x-axis and the y-axis with measures or units on both sides. So one person got a score of 1 on the depression scale and a score of 5 on the anxiety scale. So let's say we do an entire study, getting the results of depression scores and anxiety scores for, let's just say, 100 people. Okay, we can plot everybody's score on the x and the y axes, and so we have some low scores here on both depression and anxiety, a lot of people in the middle, and then some people, few people, with high scores, very high scores on both depression and anxiety. It's a very interesting way of visually presenting data. And a probability score. Probability, what is a probability theory? It addresses the likeliness of an occurrence. It's used to explain the extent of a relationship, the probability of an event occurring, the probability the event can be accurately predicted, and it is expressed as a lowercase p with values expressed as a %. So if the probability is 0.23, then p is equal to 0.23. There's a 23% probability that a particular event will occur. In research, oftentimes you will see the probability expressed as p is less than 0.05. There's less than a 5% chance that findings are due to chance. Less than a 5% probability that a particular event will occur. However, interventions that carry risk, the p requirement is more stringent. They require a very low p-value. For example, p is less than 0.0001. So we're still talking about probability theory. What are inferences? An inference is a conclusion or a judgment based on evidence. Judgments are made based on statistical results. Statistical inferences must be made cautiously and with great care. Decision theory rules were designed to increase the probability that inferences are accurate. Now we have a few words about decision theory. This is an inductive reasoning process. It assumes that all the groups in a study used to test a hypothesis are components of the same population relative to the variables under study. It's up to the researcher to provide evidence that there really is a difference at the end of the intervention. To test the assumption of no difference, a cutoff point is selected before analysis. Factors that must be considered are the study purpose, hypotheses, questions, or objectives, the research design, and the level of measurement of the data that's being collected. It requires you to be familiar with the statistical procedures used in the study, and it requires you to compare the statistical procedures used with other statistics that could have been used to a greater advantage. Are they dependent or independent groups? So we're talking about judging the statistical suitability. When you read a study and you see the results, you have to have in your mind, is this the appropriate statistics for this type of data, for this type of research design, for this hypothesis, for this study purpose? So you must consider the level of measurement of the data. This determines which statistical tests should be used. If the data is nominal or ordinal, we use non-parametric statistical tests. If the data is ratio or interval, we use parametric tests. You must judge whether the procedure was performed appropriately and the results were interpreted correctly. The judgments that are required are whether the data for analysis were treated as nominal, ordinal, or interval, the number of groups in the study, whether the groups were dependent or independent. And generalizing the findings extend the implications of this findings from the sample study to a larger population, from the situation studied to a more general situation. And you really have to be careful about how far generalizations can be made. So the generalizations are based on accumulated evidence from many studies. They are important for verification of theoretical statements or for the development of new theory. They are the basis of science, and they contribute to scientific conceptualization. Once a researcher has conducted a study, analyzed the data, and has written up the findings, the researcher will suggest further studies that could be enacted based on what they have just completed. The researcher gains knowledge and experience from conducting the study that can be used to design a better study next time. Researcher often makes suggestions for future studies that logically emerge from the present study. So if you are going to go to graduate school and you're interested in a particular topic, you should start reading the studies in that area. And at the end of the article, you will see suggestions for further studies. That might give you an idea of what kind of research you do in your graduate program. The study suggestion for further studies might be doing a replication study with a different sample. Doing a study with a different design or with a larger sample, or hypotheses emerging from the findings. And they usually suggest strategies to further test a framework in use. Okay, now we're going to switch topics and start talking about the normal curve again. What is a normal curve? A theoretical frequency distribution of all possible values in a population. No real distribution exactly fits the normal curve. However, in most sets of data, the distribution is similar to the normal curve. Levels of significance and probability are based on the logic of the normal curve. You are familiar with type 1 and type 2 errors. This is important for you to know. Type 1 error occurs when the researcher rejects the null hypothesis when it's true. So, if a researcher says, We can reject the null hypothesis. There is a difference based on my findings, and they're in error. They're rejecting the null hypothesis when it really is true. The results indicate that there's a significant difference when in reality there is not. And a type 2 error occurs when the researcher regards the null hypothesis as true, but it is false. The results indicate there's no significant difference when in reality there is a difference. And this is a table that goes through various scenarios. Okay, and I'll just let you look through that yourself. The risk of making a type 1 error. The threshold at which a statistical significance is reached is your alpha. The terms power and effect size. Power and the risk for a type 2 error. Power is the probability that a statistical test will detect a significant difference if one exists. And the cutoff value for power is 0.8. That's a minimum. And it's influenced by the sample size and the effect size. The effect size is the percent of change that occurs in the variables of interest in an interventional or correlational study. Exploratory analysis. So when you get your data, you input it into the computer into, for example, SPSS statistical package. So you have data for every subject on all the variables being studied. And you do some initial studies. You try to determine the nature of the data in the variables used to test the hypotheses, questions, and objectives. You identify outliers, and you examine relationships among variables. That's the first thing. Then you perform analyses designed to test the hypothesis, the research questions or objectives. And then you start generalizing the findings from the sample to appropriate populations. What are 5 types of results associated with quasi and experimental studies? Significant results that agree with those predicted by the researcher. That would be the ideal situation. Or non-significant results. Haven't found anything significant here. Significant results that are the opposite of those predicted by the researcher. Mixed results, where you get a little bit of both. And unexpected results. Significant and predicted results are in keeping with those predicted by the researcher, and they support logical links developed by the researcher. Non-significant results, also called negative or inconclusive results, the analysis showed no significant difference in the relationships. Results could stem from a type 2 error, and causes of a type 2 error include inappropriate methods, biased or a very small sample, and internal validity problems. Inadequate measurement, weak statistical measures, and faulty analysis. These are all things that can lead to non-significant results. Significant and unpredicted results. They're significant and unpredicted. These are opposite of those predicted. They indicate flaws in the logic of both the researcher and the theory being tested. If valid, they are an important addition to the body of knowledge. Mixed results are most common outcome of studies. One variable may uphold predicted characteristics, whereas the other does not. Or 2 dependent measures of the same variable may show opposite results. It may be caused by methodology problems, and it may indicate a need to modify existing theory. Unexpected results are relationships between variables that were not hypothesized and not predicted from the framework being used. They can be useful in theory development, modification of existing theory, and development of later studies. You hear the term serendipity, serendipitous results. These are important as evidence in developing the implications of the study. They must be evaluated carefully because the study was not designed to examine these results. This is something that you found out and you really weren't looking for it. Findings, the results of the study that have been translated and interpreted. It's a consequence of evaluating the evidence. Now, the conclusions. This is another heading that you will see in a published research report. So first the findings, then the conclusions. This is a synthesis of the most important findings using logical reasoning, creative formation of a meaningful whole from the little bits of pieces of information obtained through data analysis and findings from previous studies. You have to be receptive to subtle clues in the data and possibly alternate explanations of the data. There's a risk in developing conclusions in going beyond the data. So you can't jump to conclusions that are not supported by your evidence. Forming conclusions not warranted by the data. It occurs more frequently in published studies than one would like to believe. Isn't that interesting? Implications. That is another section. What do the findings have to do with nursing? The meanings of conclusions for the body of knowledge, nursing knowledge, theory and practice. It's based on but are more specific than conclusions, and they provide specific suggestions for implementing the findings. Significance of the findings are associated with the importance to nursing body of knowledge, and they may be associated with the amount of variance explained, control in the study designed to eliminate unexplained variance, and detection of statistically significant difference. Findings can have statistical significance but not clinical significance. It's related to the practical importance of the findings. So even though you have data that reaches the less than 0.05, it may not be that important for practice. No common agreement in nursing about how to judge clinical significance. What is the effect size? Is the difference sufficiently important to warrant changing patient care? Who should judge clinical significance? Patients and families, clinicians, researchers, society at large. I would say all three. It's a value judgment. Okay, back to probability. So if the probability is 0.23, then P is 0.23. There is a 23% probability that a particular event will occur, and the probability is usually expected to be P is less than 0.05. The cutoff point is referred to as the level of significance, or the alpha. This is the point at which the results of statistical analysis are judged to indicate a statistically significant difference between the groups. For most nursing studies, the level of significance is 0.05, sometimes written as alpha equals 0.05. For most nursing studies, 0.05. The cutoff point is absolute. If a value obtained is only a fraction above the cutoff point, the groups are from the same population. No meaning can be attributed to the differences between the groups, and the results that reveal a significant difference of 0.001 are not considered more significant than the cutoff point. So here are some levels of acceptable significance. Most of the studies that I have read and are familiar with are 0.05 or 0.01 for nursing studies. Now we are getting into some statistical procedures that I'm not sure that you had in your undergraduate statistics course, but we will go through them anyway. Okay. So performing post hoc analysis. This is necessary when ANOVA is used, analysis of variance is used in studies with 3 or more groups. Necessary with chi-square analysis, and the purpose is to determine which groups are statistically different. So generalization is the application of information that has been acquired from specific instance to a general situation. Generalizing requires making an inference. Both inference and generalization require the use of inductive reasoning. An inference is made from a specific case and extended to a general truth, from a part to a whole, from the known to the unknown. So in research, an inference is made from study findings to a more general population. You may be familiar with the chi-square test of independence. This is used with nominal or ordinal data, and it tests for differences between expected frequencies to see if the groups are alike and the frequencies actually observed in the data. Examines the frequency of the observed values in comparison to the values that would have occurred by chance were all conditions equal. This is an example of a chi-square table, male and female, regular exercise, no exercise, totals. So chi-square results indicate that there is a significant difference between some of the cells in the table. The difference may be between only 2 of the cells, or there may be differences among all of the cells. Chi-square results will not tell you which cells are different. So here are some results. Chi-square equals 4.98. Degrees of freedom is 2, and the probability is 0.05. Degrees of freedom refers to determining the part of a statistical table that's used for identifying the critical values of the test needed for hypothesis testing. And I'm pretty sure that you had that in your statistics course. Pearson product moment correlation tests for the presence of a relationship between 2 variables called bivariate correlation. Types of correlation are available for all levels of data. Best results are obtained using interval data. So correlation is performed on data collected from a single sample. Measures of the 2 variables to be examined must be available for each subject in the data set. And regarding the results, the nature of the relationship can be either positive or negative, and the magnitude of the relationship is shown on a scale from -0 to all the way up to +1. And it's a test of the significance of a correlation coefficient. Does not identify the direction of a relationship. They are symmetrical. So here, here's a little quiz for you. Here are some correlation results. Which ones are significant? Well, this one, R is equal to 0.56 with a probability of 0.03. That's quite good because it's less than 0.05, right? And the R is 0.56, which is pretty high. Now here we have a negative relationship. R is equal to, the two variables are negative related, but it's not very strong. Okay, and the probability is 0.2. So I would say this one is not very significant. Now this one, the R is equal to 0.65. That's a strong relationship, right? It's getting close to 1. And the probability is 0.002. So that's highly significant. Okay. I don't think that your course talked about R squared, because that's really an advanced statistics course. But if you see R squared, it's the variation between the two variables expressed as a percentage. Cronbach's alpha coalition, we've talked about this one before. To what extent is the measure a true reflection of the subject's responses? It tests the internal consistency of a measurement scale, and reliability of 0.7 is the lowest acceptable alpha. That means that 70% of the time you can trust the score to accurately reflect what is being measured. Factor analysis examines relationships among large numbers of variables, usually a national study. And there's so many variables, it disentangles those relationships that tend to cluster together. So it sorts the variables according to how closely related they are to the other variables. Closely related variables are grouped into a factor. So an example is used to examine construct validity of a multiple item Likert scale to measure hope in older adults. Several factors may be identified within a data set. The researcher must explain why the analysis grouped the variables in a specific way. Statistical results indicate the amount of variance in the data set that can be explained by each factor, and the amount of variance in each factor that can be explained by a particular variable. Factor analysis aids in the development of theoretical constructs, and it aids in the development of measurement scales. Regression analysis is used when one wishes to predict the value of one variable based on the value of one or more other variables. For example, to predict the possibility of passing the credentialing exam based on GPA from a graduate program. The outcome of analysis is the regression coefficient, or R. When it's squared, it indicates the amount of variance in the data that's explained by the equation. And the R square is also called the coefficient of multiple determination. Here are some regression results. R squared is equal to 0.63, indicating 63% of the variance in length of stay can be predicted by the combined effect of age, weight, complications, and sucking strength of an infant in a neonatal unit. We've talked about the scatter plot before. The t-test requires interval level measures, and it tests for significant differences between two samples. Most commonly used test for differences. An example would be to assure the reader that the experimental and control groups are not significantly different before the intervention is performed. Right? Examples of a t-test: T is 4.169, P less than 0.05. Analysis of variance, or ANOVA, tests for differences between means using variances. More flexible than other analyses in that it can examine data from 2 or more groups. Multiple versions of ANOVA are available that can be used in studies examining multiple outcome variables or repeated measures of outcome variables across several time periods. It can look at between-group variance, within-group variance, and total variance. The value that you're looking for is your F value. So F equals 9.75. P is equal to 0.002. Okay? If there are more than 2 groups under study, it is not possible to determine where the significant differences are. So then you have to do post hoc tests to examine the exact location of where the differences lie. And a Bonferroni test, Chaffee test, or Tukey test will do that. Analysis of covariance allows the researcher to examine the effect of a treatment apart from the effect of one or more potentially confounding variables. Potentially confounding variables that are commonly of concern include pretest scores, age, education, social class, and anxiety level. So they look at the variables, they look at the outcome, and they control for age, or they control for level of education. The effects on study variables are statistically removed by performing regression analysis before performing ANOVA, and it allows the effect of the treatment to be examined more precisely. So what questions are important when critically appraising statistics in a study? You will ask what statistics were used to describe the characteristics of the sample. Second, are the data analysis procedures clearly described? Did the statistics address the purpose of the study? Did the statistics address the objectives, questions, or hypotheses of the study? Were the statistics appropriate for the level of measurement of each variable? Okay, I'm just going to go back to the beginning. Okay, so this presentation is focused on Chapter 11, Understanding Statistics in Research. These were our objectives, and if you look them over, we did everything from purposes, process, probability theory, normal curve, type 1, type 2 errors, describing the results from inferential analysis, the 5 types of results obtained from different studies, the compare and contrast statistical significance and clinical importance, and what questions should be in your mind when you critically appraise a study for their statistical results, their findings, their limitations, their conclusions, and generalizations of findings. Okay, this concludes our presentation on understanding statistics in research. Kindly view this presentation along with reading Chapter 11 in your textbook. Thank you very much.